Now that you get to know the relationship between the machine code and instruction, let's dive into more about how to interpret the machine code into the binary format. This table describes the bit assignment map for ADDI assembly instruction. And if we refer to the reference manual of RISC-V architecture, and you're going to see those kind of table that describe how to interpret the machine code. As you can see, the representation of this kind of the machine code can be based on binary format instead of hexadecimal format. For this, we need to convert this value into binary format. But important point is, this binary value can be divided into several fields. Several fields means 0 to 6 bit, 7 to 11th bit, and 12 to 14 bit. Each field has different meaning. 0 to 6 bit means opcode, and 7 to 11th bit indicate destination register, and 12 to 14 bit means the functionality of this instruction, and 5th to 9th bit indicate the first operand. This is the first operand. In other words, this is the first source register. So this binary value can be regrouped based on this information, and this can be seen like this. The binary format can be regrouped based on this information. 0 to 6, 7 to 11. So please take a look at this. This hexadecimal format machine code can be converted into the binary format, and this binary value can be regrouped based on the bit assignment map. So this value can be regrouped into this one. So please take a look at this. So first, let's take a look at the OP code. As for this binary value, 0 to 6, the bit contained this binary value, that is 0011, and this value means that this is the ADDI assembly instruction. But in the RISC-V architecture, this OP code only indicate the instruction group. So please take a look at another assembly instruction, that is SLTI assembly instruction. This assembly instruction is different. Another instruction just like ADDI assembly instruction. But as for this assembly instruction, 0 to 6 bit contained this binary value. But remember that this instruction can be grouped into the same instruction group that is based on 0, 001, 0011. Next thing you have to look at is the 12 to 14 bit that represent the functionality of this assembly instruction. As for this binary value, and 12 to the 14 bit is 0. So combining the two information, you can derive that the machine code is ADDI assembly instruction. So for details of this information, I recommend you to look at the reference manual. This is name of this reference manual is RISC-V instruction set volume 1, then unprivileged architecture. So we interpret the most important part of the machine code, that is about mnemonic. Based on this information, and we can drive important the critical information that is the mnemonic for this machine code. Another important thing we have to interpret is the identify the source register and first source register. For this, we need to look at the bit 7th to 11 bit inside this value. Please take a look at this. 7th to 11th bit has the 0, 1, 1, 1, 0. If we convert this binary value into the hexadecimal format, this value is 0x14. 0x14 means x14 register. x14 is one of the general purpose register in RISC-V architecture. This register is A4 register. A4 register is in ADDI format. What I mean is those two registers are the same, but difference is to describe the way to this kind of register. This is ADDI format. This is the architecture format. From this information, we can say that destination register for ADDI instruction is A4 register. So let's look at the 5th to 9th bit inside this bit value. Please take a look at this. 5th to 9th bit has the 0, 1, 1, 1, 0. And so that this is in the binary format. Converting this value into hexadecimal format, we can have this value, that is 0x14. This indicates that the first source register is A4 register, just like the destination register. 7th to 11th bit position has the 0x14, so we can derive the fact that the destination register is A4 register. The last thing we are going to do is to check the second operand. For this, we need to refer to the bit position, the 20th bit to 31st bit. And based on this information, we can have the binary value here, 001, 00000000. And this binary value can be converted into the hexadecimal format, that is 0x200. This is considered the second operand. This information can be identified here. The second operand is 0x200. So combining all of the information, we can drive this assembly instruction from this binary value to those kind of human readable assembly instruction. So this is the way that RISC-V core interpret this machine code, and this is the important way to identify any kinds of the machine code and where those kind of the machine code can be interpreted is human readable format. This information can be based on bit assignment map in the RISC-V manual. Now we got to know about how the machine code can be mapped onto assembly instruction. We got to know how to interpret the machine code into human readable format, just like this. In this lecture, you got to know how to interpret the machine code into human readable instruction from the binary value to the assembly instruction. In summary, any machine code has the different field, several different fields with different meaning. That information can be identified in RISC-V reference manual, and you got to know how to interpret each bit position to human readable format. So we got to know about how the machine code can be converted into the binary format, and you got to know how to read those kind of bit assignment map to represent the machine code. So in this example, ADDI assembly instruction is analyzed as the example assembly instruction. The next lecture, we are going to explore another example assembly instruction, that is SUB assembly instruction.